The Big Bang Theory is the prevailing scientific explanation for the origin and evolution of the universe. According to this theory, our universe began as an incredibly hot and dense state around 13.8 billion years ago. To understand the Big Bang Theory, let's take a step back and explore the evidence that led scientists to this remarkable conclusion. One of the key pieces of evidence is the observation that our universe is expanding. Astronomer Edwin Hubble made this groundbreaking discovery in the 1920s when he observed that galaxies were moving away from each other in all directions. This led scientists to theorize that if the universe is expanding, it must have originated from a highly compressed and dense state. As we trace back in time, we arrive at a moment known as the cosmic microwave background radiation. This radiation is a faint glow that permeates the entire universe and is considered to be a remnant of the early stages of the universe. Its discovery in 1965 provided strong evidence in support of the Big Bang Theory. According to the Big Bang Theory, the universe began from an unimaginably hot and dense state known as a singularity. This singularity contained all the matter, energy, space, and time that would eventually form our universe. However, when we try to describe the conditions within a singularity, our current understanding of physics breaks down. The laws of physics, as we know them, are based on general relativity and quantum mechanics. General relativity, formulated by Albert Einstein, describes the behavior of gravity on large scales, while quantum mechanics deals with the behavior of particles on very small scales. Unfortunately, these two theories are not currently compatible when describing the extreme conditions within a singularity. In a singularity, the laws of physics break down because the density and temperature become infinitely high. General relativity predicts that the singularity is a point of infinite density, meaning that matter and energy are compressed into an infinitesimally small space. However, when infinities arise in equations, it suggests a limitation in our current understanding. This breakdown of physics within a singularity indicates that there might be a need for a more comprehensive theory that combines general relativity and quantum mechanics. This theory, often referred to as a theory of quantum gravity, would help us understand the behavior of matter and energy under the extreme conditions of a singularity. Various theoretical frameworks, such as string theory and loop quantum gravity, attempt to bridge the gap between general relativity and quantum mechanics. These theories propose new mathematical models that could potentially describe the nature of a singularity and what existed before the Big Bang. Cosmic inflation refers to a rapid and exponential expansion of the universe that occurred shortly after its birth, stretching it from subatomic scales to macroscopic dimensions. But what caused this extraordinary expansion? The idea of cosmic inflation was first proposed in the 1980s by physicist Alan Guth and later developed by Andre Linde and others. It was introduced to explain several puzzling aspects of the universe, such as its overall uniformity and the absence of certain cosmic relics. According to the theory of cosmic inflation, the universe experienced a brief period of incredibly rapid expansion, driven by a hypothetical field called the inflaton field. The inflaton field is distinct from the more familiar fields like electromagnetic or gravitational fields. It is a scalar field, meaning that it has a single value at each point in space. During cosmic inflation, the inflaton field was in an unstable state. As the universe expanded, the energy stored in the inflaton field was released, driving the exponential expansion. This rapid expansion had profound consequences for the structure and properties of our universe. One of the significant effects of cosmic inflation is that it smoothed out irregularities and inconsistencies in the early universe. Prior to inflation, the universe was a hot, dense, and turbulent soup of particles and energy. However, during the inflationary phase, quantum fluctuations in the inflaton field got amplified and stretched across the universe, becoming the seeds for the formation of galaxies and other cosmic structures. Cosmic inflation also explains the remarkable isotropy and homogeneity observed in our universe. Before inflation, different regions of space could not have had enough time to interact and reach a state of equilibrium. However, during inflation, these regions were brought into contact with each other, leading to the uniformity we observe on large scales today. The multiverse theory stems from the recognition that our universe appears to be finely tuned to support life as we know it. Numerous fundamental constants and parameters, such as the strength of gravity or the mass of elementary particles, seem to be delicately balanced to allow for the existence of complex structures like galaxies, stars, and life itself. One way to explain this apparent fine-tuning is through the concept of the multiverse. The multiverse suggests that there are a vast number of universes, each with its own unique set of physical laws and properties. Within this vast ensemble, the values of fundamental constants and parameters vary from universe to universe. In some of these universes, the values may not support the formation of stable atoms or the emergence of life. However, in a fraction of the multiverse, the conditions might be just right for the emergence of complex structures and life as we know it. The multiverse hypothesis has gained traction through various theoretical frameworks, such as string theory, inflationary cosmology, and quantum physics. These frameworks suggest that during cosmic inflation, regions of space could undergo a process called eternal inflation, leading to the creation of new universes within a larger multiverse. Inflationary cosmology suggests that during the rapid expansion of the early universe, quantum fluctuations can cause some regions to inflate into separate universes, each with its own unique properties. These universes would exist alongside our own, but due to their vast distances or different physical laws, they would be inaccessible to us. String theory, a framework attempting to unify all fundamental forces and particles, proposes the existence of multiple dimensions beyond the familiar three spatial dimensions and one time dimension. Within these extra dimensions, other universes could exist, each with its own set of physical laws and properties. According to quantum mechanics, particles can spontaneously appear and disappear within a very short time span due to the inherent uncertainty in their properties. This phenomenon is known as particle pair creation and annihilation. These pairs of particles, called virtual particles, borrow energy from the vacuum of empty space before annihilating each other and returning that energy back to the vacuum. Quantum fluctuations arise from these fleeting appearances and disappearances of virtual particles. They are an inherent property of the quantum nature of reality, occurring at the most fundamental levels of existence. These fluctuations are observed and confirmed through experimental phenomena such as the Casimir effect. Now, how do quantum fluctuations potentially connect to the birth of our universe? The theory suggests that during the early moments before the Big Bang, the universe existed in a state of extreme energy density. Within this intense environment, quantum fluctuations played a crucial role. According to certain models, a tiny region within this highly energetic state experienced a temporary fluctuation, creating a bubble or a quantum fluctuation event. This bubble, containing an enormous amount of energy, could have triggered the rapid expansion that led to the Big Bang and the subsequent evolution of our universe. In this scenario, the energy stored within the quantum fluctuation event caused a rapid expansion, analogous to the inflationary phase we discussed earlier. As the bubble expanded, it cooled down, and matter and energy began to condense, eventually leading to the formation of galaxies, stars, and other cosmic structures. The ekpyrotic universe theory is rooted in the framework of string theory, which suggests that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings of energy. String theory also suggests the existence of extra dimensions beyond the familiar three spatial dimensions and one-time dimension. In the ekpyrotic universe scenario, our universe is conceived as a three-dimensional brain floating within a higher dimensional space. A brain is like a sheet or membrane that can move and interact within the higher dimensional space. According to this theory, there was another brain parallel to our universe. In the early stages, the two brains moved towards each other within the higher dimensional space. As they approached each other, gravitational forces between the brains intensified, leading to a dramatic collision. This collision caused an immense release of energy, triggering the birth of our universe. The energy released during the collision set in motion a phase of rapid expansion and subsequent cooling. This expansion is analogous to the inflationary phase discussed earlier. As the universe expanded and cooled, matter and energy gradually formed, eventually leading to the emergence of galaxies, stars, and other cosmic structures. A framework that combines quantum mechanics and general relativity to propose an alternative explanation for the origin of the universe. According to loop quantum cosmology, the universe undergoes a cycle of contraction and expansion, with each cycle preceded by a significant event known as the Big Bounce. Loop quantum cosmology stems from the effort to reconcile the principles of quantum mechanics with the theory of general relativity, which describes gravity as the curvature of spacetime. Quantum mechanics governs the behavior of particles on small scales, while general relativity describes the dynamics of spacetime on large scales. In loop quantum cosmology, the universe is viewed as a collection of interconnected loops or networks of fundamental building blocks known as quantum loops. These loops represent the discrete structure of space and time at extremely small scales, beyond what general relativity can describe. According to loop quantum cosmology, the universe undergoes a cycle of contraction and expansion, similar to the concept of a cosmic breathing. Each cycle begins with a phase of contraction, during which the universe becomes increasingly dense and smaller in size. As the universe reaches a critical point, the effects of quantum gravity become significant, leading to the occurrence of the Big Bounce. The Big Bounce is a pivotal event where the contraction phase reverses and the universe transitions into an expanding phase. Instead of a singularity like the Big Bang, where the universe is infinitely dense and spacetime breaks down, the Big Bounce represents a smooth transition from contraction to expansion. During the contracting phase, as the universe becomes smaller and denser, the effects of quantum gravity dominate, preventing the universe from collapsing into a singularity. The discrete nature of space and time described by loop quantum cosmology ensures that spacetime remains resolved and avoids the breakdown associated with singularities. The critical point at which the Big Bounce occurs is characterized by a minimum limit on the universe's size, beyond which it starts to expand. The bounce is driven by quantum effects that cause the universe to rebound and enter an expanding phase, similar to the conventional Big Bang scenario. By incorporating the principles of quantum mechanics and discrete spacetime into the cosmological framework, loop quantum cosmology provides an alternative explanation for the origin and evolution of the universe. It suggests a cyclic nature, where the universe experiences an infinite series of contractions and expansions, each preceded by a Big Bounce. While these theories provide intriguing possibilities, the truth remains that we currently lack concrete evidence or a definitive answer to what existed before the Big Bang. It's a tantalizing mystery that continues to drive scientific exploration and fuel our curiosity about the origins of our universe. So, keep exploring. Keep asking questions, and who knows, maybe one day, we'll unlock the secrets of our cosmic origins. Thanks for watching, and don't forget to subscribe for more captivating content like this.